Okay. Welcome to this session in Zerynth Continuous Learning series. My name is Karim. I am an embedded software developer. And in the session, we're going to mainly tackle some tips and tricks involving debugging on embedded systems. Generally, I've divided this presentation into two parts. Essentially, I want to address two things in this presentation. In general, I want to address some challenging concepts and topics related to embedded development in particular. And then we're going to take a look at a bug related to interrupts on ARM Cortex M4 microprocessors. So we're going to make an introduction into interrupts. How are they implemented on Cortex M4, and how could we debug this problem? And then we're going to look at some interesting C code snippets. So in general, I want to address two things. I want to talk about some general concepts and some general topics in embedded systems. These topics will include something like operating system, for instance. Why do we use operating system on embedded systems? How could we use them, etc. And we're going to also tackle another cool challenge in embedded system, which is the code size. Typically, when you're developing embedded systems, you go into this problem often. Then we're going to start developing. So essentially, I will talk about some topics in general, introduce some new ideas and concepts, and then we're going to dive into the debugging session. So okay, it's going to be a long presentation, so get something to drink and then let's start doing it. Okay, so let us start from the beginning. So what is the difference between a general purpose system and an embedded system? So general purpose systems, for instance, are like PCs, for instance. So these are general purpose systems. And embedded systems might be any system that is responsible for a certain task. That means controlling some kind of motors, doing some kind of calculations, sending some data to the cloud. So let's first talk about the general differences between general purpose systems and embedded systems. So embedded systems are generally, they are dedicated to a single purpose or a single task. That means that they are optimized to the lowest level to operate and to execute this single or these set of tasks. On the contrary to general purpose systems. So general purpose systems are made to accommodate numerous tasks. For instance, PCs, they are made to accommodate whether the user will run heavy computational programs or just browse the internet with some light applications. So that means that general purpose systems tend to have a large amount of resources, a large amount of memory, large computational or strong computational power, a different instruction set than the embedded systems wise. So typically embedded systems are made, custom made or hardware wise custom made to fit each application. So you run into different set of problems when you're developing an embedded system. For instance, you run into some design limitations. So you might work on a project that involves some needed hardware, some specific hardware. Or you might run into some stability issues because embedded systems tend to run typically forever in a stable fashion. So you need a device, for instance, that will monitor some kind of data for instance, if you're developing a weather station, you might need it to get some data to process this data and send it to the cloud, but you needed to do these things in a stable fashion. That means continuously running, and it should run like give the same performance on the first day and on the last day. So stability wise, this is something that's really important. And security wise, you run into this issue with embedded systems, especially in the IoT field. So you're making devices that's connected to the cloud. How are you sure of this secure connection? How could you secure your code on the microcontroller? Because you're developing these devices in the field. You're leaving them in the field, essentially. You're deploying them, you're testing them, and then you're leaving them in the field. So how could you make sure that even security-wise, your code or your firmware is secure? So you run into different set of problems. That's why typically embedded systems are very optimized in terms of processing power and in terms of RAM. So for example, in a project, you might use something really simple or something really optimized, such as the ATtiny 85 microcontroller, which is an 8-bit microcontroller that has just an 8 kilobytes of RAM, that has just 512 bytes of RAM and then 8 kilobytes of flash. So write a code on this piece of hardware, on this microcontroller, needs to be very optimized just to fit into these restrictions. But it's not a weak microcontroller. It has all typical needed peripherals, such as GPIO to control some devices. It has serial communication to communicate with other devices and sensors. It has ADC to get some data. It has interrupts. It has power management to run on battery powered devices. So you might use something like this, or you might use something like the STM32, which is a very powerful microcontroller that, for instance, runs on a 400 megahertz clock speed and has interface for USB and for CAN, for automotive, and for graphics, for human interface HMIs. So depending on the project that you're working on, it has to be customized to this application. That's why the code that should be written on the microcontrollers should be also optimized. You cannot just use the same techniques that you use on general purpose systems and then deploy them to the microcontrollers. For instance, embedded systems tend to deploy something called the super loop. So the super loop is typically a loop that runs infinitely or forever, essentially. Something like this, if we are writing some sort of a very abstract code, we might initialize some drivers. That means we might initialize some code drivers, some codes related to sensors. And then we need to check the sensor, check the temperature, calculate the temperature, and then send the data to the cloud. But we've included these three lines of code in a while loop. So this code will run forever. So essentially, the microcontroller has only one function, which is to get the data, calculate the data, and send it to the cloud, and that's it. So this is the super loop. So the super loop means that it's a loop that will run indefinitely. It will run forever. So one might ask the question, what happens if there is no loop? So what happens if essentially we just put the code like that? We initialize the drivers, we check the temperature sensor, and we calculated the temperature and control the motor, for instance. So what happens if there is no loop? That's the question. What happens is that the microcontroller typically will take the source code, will compile the code, and then will burn the code to the microcontroller and put it in a piece of memory called the flash. And then it will start to execute. It will execute this line of code and then this, and then calculating the temperature and then controlling the motor. And then it will calculate whatever is next in the memory. And that's the problem. If we don't have an infinite loop, essentially, we are just going to continue execution, whatever is written on the next instruction or in the next memory location on the memory. So, of course, in the recent microcontrollers, especially on the ARM family, this problem has been dealt with during the startup files. But what I want to point to in this slide is that typically in embedded development, we are using infinite loops or super loops just to avoid this stability issue, just to make sure that we are running infinitely in this piece of code, in this confined lines of code. Okay, so we've written a C source code. Right now we need the machine code. So does the microcontroller understand our C language? No, the microcontroller does not understand that language. So we need something to convert our source files to the machine codes. We use two things. We use the compiler and then we use the uplinkers. So what are the compilers and what are the uplinkers? The compilers are a piece of software that is responsible for converting the source code into something called an object code. So typically a compilation is a multi-stage process, but in very simple terms, it is something that takes the C source codes that you write and then convert them into object codes. Then these object codes are then inserted or are then sent to the uplinker, and the linker takes these object codes and then converts them to the machine code that the microcontroller understands. So simply, our C source files go to the compiler, and the compiler outputs an object code. Then these object codes go to the linker, and then the linker links many object codes and then produces the machine code. This code is what the microcontroller understands, essentially. So in the compiler, compilation is a multi-stage process. So it involves first parsing the code. So the compiler has to figure out what have you written, essentially. What's the meaning of this? Is this the correct function, etc. So this is the compilation process. That's the first part, is actually parsing the code. The second part is optimization. So the compiler has to optimize your code, and typically it can have many options. So the compiler will ask the question, what do you essentially want? Do you want the code to be fast in terms of performance, or do you want it to be efficient in terms of code size, or do you want it to be something in the middle between this and this, or do you want the compilation time to be slower? So there are many options for the optimization during the compilation phase. And then the last part of the compilation is code generation, or the object generation. Then the linker will take these object codes that have been produced by the compiler, and then the linker will take these object codes and then produce the machine code. So the linker, as we can see, will take many files. We're not going into the details of the outputs of the compilation process and the outputs of the linker and how does the linker does that. But what we are concerned with right now is that the linker takes many files, many of which are output of compiler, takes them and then produces an ELF file, a binary file, and a hex file. These are the files that the microcontroller can understand. So in general, what have we said so far? We have said that embedded systems are in nature very different to the general purpose systems. That's why they need special development or different kind of development. That means a different kind of codes, essentially. So we write some C source code. This code goes into the compiler and then the uplinker, and then is converted to the machine code that the microcontroller can understand. So let's have a look at some cool challenges that are related to embedded development. So let us suppose this scenario. You are a software developer and you are assigned to develop a high precision surgical devices. So essentially you are developing hardware and software for this medical device. This medical device will, for example, do operations. So these devices, one of the main requirements of these devices is to have minimum to no time latency, just as minimum as possible. So what is the meaning of time latency? Is that the time between pressing a button, for example, and the result happens. So this time latency. You need to achieve a response time in milliseconds to microseconds if possible. So what we are talking about right now, we are talking about some cool challenges that are related to embedded development. So in this scenario, you are a software developer. You're developing a medical device that should operate timing-wise in minimum time latency, in milliseconds. So we are making a device, or we're developing a device that should react and respond to the input in very limited time fashion. So how could we go on about that? Like what could we use? Essentially, developers use something called real-time operating systems. So we are going to use operating systems on microcontrollers, and operating systems are a very interesting concept, especially on microcontrollers, because microcontrollers have very restricted resources in terms of memory, in terms of processing power, etc. So to tackle this problem, let's have a look at the operating systems itself. So let me ask a very brief or wide question. What's the difference between operating system on the laptop or on the PC and the operating system on the car? So what are the differences between the operating systems on the cars and on the automotive devices? The operating system that runs the adaptive cruise control, that like makes the car typically stick into one lane, for example, in the modern cars, etc. What's the difference between those and the operating system on the PCs, on your PC, for instance? The main difference between them is that operating systems on PCs tend to be developed and optimized to suit the needs for the PC user, which are running multiple programs together. Typically, PC users do not care about response time, so nothing happens if you try to open a Word file and you waited 10 seconds. No problem with that, but there is a huge problem if this happens in the system on your car. If you wanted to open an airbag, for instance, and 10 seconds is the delay, or is the latency, or is the response time, then this is a huge problem. So we're going to look at the differences between the operating systems that run on embedded systems and on general purpose systems. So the first major feature of operating systems on PCs, for instance, are that they tend to run multiple tasks, but they use time-based scheduling. And I'm using very simple terms and I'm simplifying things already, but in general, they use time-based scheduling. So what is the scheduling? The scheduling is the decision of who should run next. So for instance, you have your browser open, Google Chrome, you have a Word document opened, you are listening to some music. These are three programs. So who should run next is the scheduler decision. So scheduling means the arrangement of the tasks, who should run now and who should run next. Time-based scheduling means that our CPUs, the operating systems that we use, typically give each task a certain amount of time equal to the others. So for example, I might give this program 10 milliseconds, 10 milliseconds, and 10 milliseconds, and then I'm going to go around again. So this is one of the major features of operating systems on the PC. Another major feature is the response time. As I said, as you increase the open tasks on the PC, the response time gets longer. So the 10th program that you opened has a response time slower than the 20th. So in essence, the first program that you open is going to be the fastest. And as you increase the tasks and as you increase the processes running, you're going to have a slower response time. This is a very big drawback in the operating systems on your PCs. So it has unpredictable response time, essentially. Going to the real-time operating systems, you're going to find that it is completely the opposite. It has a determinable, even at the bare minimum, a worst case calculated response time. So in real-time operating systems, or on the operating systems that run on the automotive industry or on the cars, for instance, they tend to have a determined response time. Why? Because they don't use a time-based scheduler. They don't give a certain amount of time to each task. They use priority-based scheduler. So in real-time operating systems, as we see here, predictable or calculated response time is achievable because they're using a different kind of scheduler. They're using priority-based scheduler. So priority-based scheduler means that the decision of whose task is going to run next mainly depends on the priority. Do you have a higher priority than the current task or not? That's the big question. So if we look on the right, we find that, for example, this example is a low priority task is running. But the interrupt service routine, which is something that has a very high priority, now it needs the CPU now. So the scheduler basically runs this interrupt service routine. When it is finished, it's going to go to the lower priority, which is a high priority in the blue, run that, and then it's going to go to the lowest priority. So as you can see, it's not time-based as the general purpose systems. So what I want to say, essentially what I want to say is real-time operating systems tend to have predictable response time or calculated response time because they tend to have priority-based scheduling. So it tend to have a scheduler that runs on priorities. So everything in your system will need to be prioritized, essentially. The third feature of operating systems that run on microcontrollers are that they are optimized. So real-time operating systems are optimized for low resources, low flash memory and low RAM, for instance. And this begs the question, what does the real-time part means? So I'm saying real-time operating system. Real-time here means that there are deadlines and that we are concerned with the response time and with the latency. But that does not mean it's fast. So real-time does not mean fast. Fast is very relative. What real-time means is that we can calculate the timing of essentially each operation. So just to summarize, the key features of real-time operating systems is that the response is in a timely manner or a predictable. At the very least, worst case scenario could be calculated. So they respond in a timely manner to unpredictable external events, and that's the important part. And that they are priority based. But this begs the question. So microcontrollers are very limited in resources. So what happens if two tasks wants to access the same resource? So for example, you might work on microcontrollers that have a certain amount of timer preference. Timer preference is something that is related to timing. It's related to doing a certain task every 10 seconds, every second, whatever. So timer is essentially a resource. So what happens if we have two tasks that needs to execute this same resource? We run into a problem called shared resource problem. Essentially, what we are talking about is that there are multiple tasks that want, in the same time, they want to access the same resource. So this is a key feature of real-time operating system. How do we solve this issue? It's a complicated and long story, but just to simplify everything, we are going to make keys and we're going to make locks. So as an abstract term, I would, for example, on this shared resource, I would lock it and give the key to a task, let's say task 1. And then task 1 consumes the resource, do with it whatever it wants, and then when it finishes execution, it should unlocks the resource. So the other task finds that the resource is now unlocked and then starts executing it. For those who are familiar with real-time operating systems, I'm talking about semaphores and mutexes and that stuff. So essentially, real-time operating systems deal with the shared resources with sort of implementation related to locks. That means locking a resource, giving the key to a task or to a thread, and then when the task finishes, this task unlocks the resource. So the other tasks can come to this resource, execute it, and do with it whatever it likes. So what are the examples of real-time operating systems applications? So like, where are the operating systems, where are the real-time operating systems used? They are used from circuit boards of surgery tools to missile guiding systems to manufacturing of safety systems to automotive systems in the cars. Basically any system that requires an immediate action in a nearly defined time. So even if you're making a manufacturing line where there is something happens every time interval, for example, you're making a manufacturing line that makes a bottles or closes the lids of bottles. This process should happen every 10 milliseconds or every 50 milliseconds. And this defined requirement or deadline is what makes the developer use a real-time operating system. Just to point or just to make or just to show you guys an example of real-time operating systems, this is a piece of code that is an example of using FreeRTOS, which is a real-time operating system running on a Atmel microchip SAM microcontrollers. So as you see here, basically this is a FreeRTOS example. The microcontroller will start running from the main function. So it will start executing atmel underscore start underscore init function, which has some initialization drivers we're not concerned with, and then it's going to execute task led create. So what does this function do? It's going to go to task led create and it's going to create a task essentially. So what I'm doing here is that I'm telling the OS create a task that will run the function called task led. So essentially I'm not telling the microcontroller to run this function. I'm telling the operating system to put this function in his list of tasks essentially. So as of this line, the task hasn't started yet. The task has not been executed yet. The task will be executed when the microcontroller starts executing vtask start scheduler. So essentially, I've put this slide just to show you an example of a real-time operating system running. So the main difference is that I'm dealing with the operating system. I'm letting the operating system decide which task to run, how to synchronize between these tasks, what happens if multiple tasks starts using a shared resource or something. If I don't use a FreeRTOS, I would just call this function, which is a task LED. So that's the difference. If I don't use a FreeRTOS, for instance, I would just put task LED in the main, and that's it. I hope that this difference is shown. Just to show you how Zerynth ecosystem makes it easier for developers to develop multi-threaded applications. This is the code example of a multi-threading example on Zerynth Studio. So Zerynth is an operating system that runs on Zerynth OS is an operating system that runs on the microcontrollers, 32-bit microcontrollers, that enables developers to develop Python and C hybrid applications. That means abstract and Python IoT applications with a very minimum or very short time development. So if you're developing IoT applications, if you're developing industrial applications, manufacturing applications, anything like that, if you're connecting your devices to the cloud, you would need to have a minimum development time to have a faster time to market essentially. And Zerynth tools typically provide these tools for the developers. So for example, this is a multi-threading example. So in this line thread, I'm basically making a thread. So just like making a task, I'm making a thread with the function thread function, which is this function, and it will be running every 500 milliseconds because that's the sleep, which is the argument. So as you can see, Zerynth provides simplistic, efficient way to develop your 32-bit microcontrollers without having to deal with all of the hassle or all the level details of the FreeRTOS. If you want, you can configure, of course, the priorities and all of that stuff related to the FreeRTOS layer. But what I want to show here is that Zerynth provides a simple way to program your applications essentially without having to deal or without having to spend long time on the underlying layer of RTOS, of configuration, of porting, and all of that stuff. So this is the operating system on embedded systems in general. So we have talked about real-time operating systems. We have talked about the difference between general purpose operating system, such as the operating systems on laptops, and the operating systems real-time, such as the ones running on cars. We talked that the real-time operating systems tend to have priority-based scheduler. So they tend to give a defined or a controlled response time. Then we talked about sharing a common resource between tasks and how we could synchronize that. Then we give some applications, and then I showed you an example of a real-time operating system example. So the second cool feature or the second cool example of the firmware size optimization of the second cool challenge of embedded systems is the firmware size optimization. Let us look at this scenario. You are a project leader of a highly successful consumer product. One day you're asked to upgrade all of the devices in the field to add the latest must-have feature. So essentially you have a product, you have a code, and you want to add a certain feature. However, when you attempt to compile the new code, you see the message that the region ROM overflow. So essentially, ROM is the piece of memory that is responsible for saving your code. So when you compile the new code, you would find that you don't have enough code or you don't have enough memory, for instance. So how could we go on about that problem? I mean, this is a problem that is strictly related to embedded development because you are dealing with microcontrollers that are very strict and very optimized in terms of the available memory. You have a few kilobytes of RAM and a few megabytes, if any, of flash. So normally you run into these problems when you're developing large applications that involve a lot of libraries, a lot of sensors, a lot of data. So how could we optimize our code essentially to reduce the firmware size or the code size? So this is a typical message that you might run into when you're compiling the code on the ARM-based microcontrollers. So essentially, the goal of any embedded system is to make the product run on the lowest cost of production version. So what that means is that I don't care if the product runs on a proof of concept. That doesn't mean anything, because the transition from a proof of concept to a production or a product is huge and it's very big. So the goal of any embedded system is to run on the most optimized production version. That means that if you can optimize the code to, instead of having a size of 200 kilobytes to 100 kilobytes, that's better. If you can use less RAM, if you can make it more efficient, if you can make it more fast, run in a more performance-wise faster, that's better. So we are going to look at the firmware optimization, firmware size optimization, essentially on 3 levels. We're going to optimize the code. We're going to optimize, we're going to provide configuration for the compiler, and then we are going to optimize on the linker. So in this problem, essentially we want to optimize the code size that is going to be burned to the microcontroller. We are going to do that on 3 levels. We're going to optimize the code, the compiler, and the linker. So let's start with code optimization. What techniques could we do to optimize the code? Like what things should we write and what things that we shouldn't write to essentially result with the same functionality but with a lower code size? One of the things that we should not do are the inline functions. So what are the inline functions? The inline function is a definition keyword that is used in the declaration of functions. Essentially, what I'm telling the compiler is that this function should be compiled or should be executed in a fast manner. So instead of calling this function, going and calling this function, I want to copy the content of the function and bring it back here. So inline means that the content of the function, basically what the function does, should be copied and put here, essentially. So what does that do? That makes the code run faster because the code is copied and put here. So I don't have to leave this function, leave this context, and switch and call and execute this function. So it makes the execution faster, but it makes the code size larger because essentially I've made 2 copies. I've made a copy of the function here and a copy of the function already over there, whatever it's defined, wherever it's defined. So the resulting of using inline function will be that we are running faster programs, but essentially we are making the size of the firmware larger, which we don't want in this particular case. The second thing that we should notice or focus on are table lookups, which are the switch cases, for instance. So the switch cases are basically you are searching, for example, for a certain value on a variable. So you have 10 or 20 cases. So putting them without an order might be not the best optimized way, because essentially the best optimization is to put the cases in a manner that is related to the relevance. So for example, if you know that a certain value will be repeated or will be the output most of the times, just put it as the first case. The third thing we might do to optimize our code is to use hand-coded assembly. So we might, in some circumstances, tend to code some pieces of code in assembly just to be as optimized as possible, because assembly is the lowest level to the hardware, to the microcontroller. This is the lowest level that we can write, and this is the most optimized level. Just as an example, FreeRTOS tends to have many assembly codes embedded within the C codes. So this is a thing that is commonly used in FreeRTOS, for instance. Then we can optimize, for example, arithmetic operations. So there are a ton of operations that could be that we can discuss later, which are related to achieving the same functionality but with a lower program memory. So for instance, on the right, I'm using a single definition, which is a equals to b minus 1 times 3 multiplied by 3, and on the right I'm using a definition of a equals to b minus 1, and in the next statement I'm using an addition instead of multiplication. So both of them achieve the same output, but on the right they use the half of the program memory. So there are tricks like that to reduce the program memory size. But the best way or the best option is to use a properly configured compiler. So what compiler typically provides a bunch of options for the developer. We're going to see these options now. So we will focus on ARM GCC because we are going to develop some codes on debug some code on the ARM based microcontroller. We're going to use the GCC ARM compiler and debugger. Typically, code size tend to be a trade-off. So compilers typically provide a bunch of options, but they are customized in a way to be a trade-off. So if you want large performance, you would have to leave the code size. If you want smaller compilation time, this would result in a larger code size, for instance, and some like these kind of trade-offs. So we are going to pick an example, run a bunch of options, and we're going to see how does the code size react to these options. So we are going to use the example from FAT/FS USB from ChibiOS that is as an example for STM32F1 microcontrollers. Let's disable all optimizations and build, and then we are going to result with a hex file that is comparable to 7273 kilobytes. So what are the options of the compiler? So what options do compilers provide essentially? Compilers provide 4 options. You can compile your code to give you optimum performance. That means the speed at which the program executes. Or you can optimize the compiler to give you optimum compilation time. That means smaller or shorter compilation time. You can optimize the code for code size, smaller code size, that's what we are trying to achieve in this scenario. And we can compile for debuggability, how easy can a program be debugged essentially. So let's translate these options to arguments. So O of 0 is the debuggability, which is the default. So that's a very important piece of information, because if you don't define any definition for the compiler, it will debug for compile time and debuggability, which is not really the best optimized way. So O of 0 is the default, which is compile time and debuggability. O of 1 is the performance. O of 2 is more performance, so it's going to be faster, but this will result in larger code memory. O of 3 is performance at all cost. O of S is optimized for code size, and this is what we are trying to achieve in this example. And O fast is the fastest, but this may lead to invalid programs, so take care with using this operation. So let's first compile our example with O of 0. So O of 0 results in 108 kilobytes of code. Then let's try O of S. So remember that O of 0 is the default, and O of S is optimized for code size. So if we compiled for O of S, we would result in 61 kilobytes. So that's 47 kilobytes smaller in code memory. So essentially, we saved half of the memory size just by using the proper configuration for the compiler. So what happens if there are some parts of your code that needs to be optimized for performance and another part of the code optimized for code size? You can just use #pragma to optimize this part of the code for O of 3 or O of S or whatever. Then the last stage of optimization is the dead code optimization, and this is done by the linker. So the linker is the only stage at which we can eliminate the dead code. So what is the dead code? The dead code is the code that never gets called. So typically when you're using large libraries, it has many features, but you will not use all of them essentially. So the linker is the one that brings in all the pieces of the hardware or all the pieces of the software, and it can look at the pieces of the software that are not used essentially and eliminate them. So that code optimization is done by the linker, and it will reduce the code size even more. So after the linker optimization, we are essentially from 108 kilobytes of code to 54 kilobytes of code. So less than half, essentially less than half of the program memory size, just by very simple and very efficient optimization. So that was firmware code optimization. Now we're going to debug an interrupt related bug. So let's introduce interrupts, and then interrupts on ARM Cortex M4 microprocessors. So scenario number 3, you are developing a weather monitoring and control station, and there is a critical temperature measurement that needs to be checked periodically. So if the temperature is above a certain value, you need to execute a certain code immediately. So how can we go on about that? I mean, you have a piece of hardware that needs to check for a sensor data every 10 seconds, every 10 milliseconds, whatever. But if this happens, you need to stop whatever you're doing, go execute this piece of code. When you come to think about it, you have two ways. You can either put a conditional in the code that continuously checks if the sensor data has been or has reached this critical value or not. If it has reached this critical value, it will go on and execute the critical code. So it will just go on forever. So essentially, part of the program is continuously checking for this sensor data. Or you can use interrupts. So interrupts is basically telling the microcontroller, this sensor is very important. Whenever this value changes, tell me. And then the microcontroller could go on and execute other stuff. And if this very important sensor value changes, I'm going to stop whatever I'm doing, go execute this important code, and then go back. So these are interrupts essentially. Interrupts are very important or critical pieces of code that needs to be executed now. So the microcontroller will leave whatever it is doing, go execute this piece of code, which is called service routine, and then return back to whatever it was doing and continue execution. So essentially, polling is a continuous monitoring of a status of a variable or a sensor or whatever. So we might write polling as something like this. In the infinite loop of the microcontroller, we will check continuously for the value of the temperature sensor. So if the temperature sensor is above a certain value, it is going to execute this important thing. If not, then it's going to execute other things. However, in the interrupts, I'm not defining it like that. In the interrupts, I am basically doing some normal operations, my normal code, and if something happens, it will be defined somewhere else, and it will stop whatever it is doing and go execute this very important code, which is the service routine. So the interrupts essentially are marked events that requires immediate attention. Interrupts request the processor to stop performing the current program and take time to execute the special code and then go back to the current program. But there are multiple interrupt sources. You might have interrupts from the pins or from a certain GPIO level pins, or you might have interrupts from the timers, you might have interrupts from the ADCs. So how does the microcontroller know exactly which function to execute? So let's dive deep into the ARM Cortex microcontrollers and let's see how are interrupts implemented. Interrupts on ARM Cortex M4 use something called interrupt vectors or interrupt vector table. So what is an interrupt vector? Interrupt vector is the address of the function that is related to the interrupt, just to put it simply, or the ISR essentially. So the interrupt vector is an address. This address points to the function that should be executed whenever the interrupt is triggered. So typically microcontrollers tend to have something called interrupt vector table. So this table is essentially a table that has addresses that correspond to the functions These functions should be executed whenever this interrupt is triggered. So priorities such as a reset priority, for instance, this is a very important interrupt, because whenever we press reset on the board, this triggers the reset interrupt, which stops whatever the microcontroller is doing and then resets the board. So there are kinds of interrupts such as harmful interrupt, cystic interrupt, and there are peripheral interrupts such as the timer, for instance. I can set the timer to execute the interrupt code every 10 milliseconds, every second, whatever. For example, the STM32F4 has a bunch of interrupts related to external interrupts. For example, for the timers, as we can see here, global interrupt, for the flash, for the watchdog timer, etc. So let's have a look at the SAM E54. So let's have a look at the interrupts for the SAM E54 and then the UART example. How are the interrupts implemented for the UART? So this is the SAM E54. Okay, if we look at the startup file of the SAM E54, this is the startup file for the microchip SAM E54 explained Pro board. So these are all the interrupt, the ISR's definitions, and as you can see, it's attribute weak. These are all the definitions that basically, if these functions are defined elsewhere, it's going to execute there. If it's not, it's going to execute dummy handler. So as you can see, these are the interrupts that I've talked about: the cystic interrupt, the usage fault, non-maskable interrupt, and if we can go down, you can find the reset handler. So the reset handler, which is this function, this is the function which is called whenever the microcontroller is powered on or whenever you reset the board. So this is the reset handler essentially. And as you can see in the reset handler, it does a bunch of operations and then it branches to the main. So it goes to the main function of the code. And this is the dummy handler that basically is the hard fault handler if you haven't defined hard fault handler. So let's have a look at the serial driver of the serial driver of the Atmel SAM E54. So let's open MPLAB. Okay, so this is the MPLAB, which is the official integrated development environment for microchip. So if we open, for example, it's a little bit heavy. So if we open any example that uses the serial, let me show you the driver. Let's see how are the interrupts implemented for this specific board in the Atmel software framework. So essentially, as we can see here, this is the flash driver, and this is the serial driver. This is the IO driver. You can find the target IO, which is the serial or the UART driver. You can find that basically it initiates the clock, it initiates the serial driver, and I want to show you essentially the UART, the interrupts. So okay, so as you can see, this is the UART this is the UART initialization, and there is a function here to call essentially this is the set IRQ state, which is the interrupt state, and then there are functions of read and write, and then there are Rx done callback and Tx done callback. So these are the functions that will be called when the UART finishes sending or when the UART receives something. So this is an interrupt. This is an example of interrupt, which is when the UART sends something, it's going to essentially leave whatever it's doing, go to the interrupt to the UART, execute this function, and then go back to do whatever it is doing. So this is an example of the interrupts in the UART for the Atmel SAM E54 Explain Pro. So heading back to this slide, let's have a very important question. So are all interrupts equal? So is there an interrupt more important than another? Yes, there are more important interrupts essentially, because every interrupt, and as we've said before, it is prioritized essentially. So every interrupt must have a priority and every task must have a priority. So this depends on the priority levels of the microcontroller. For example, this board, which is the SAM E54, has 3 priority bits. That means you have from 0 to 8 priority levels. So you can have a priority of 0, 1, 2, 3, 4, up to 8. With being in mind that priority 0 is the highest priority. So the less numerical value, the highest priority. So it's a little bit confusing, but you get used to it. Essentially, since we have 3 priority bits, that means you have 3 bits. So 3 bits can either be 000, 001, 10, essentially the whole thing. So you have 8 levels. Just as an example, how could we set a priority of an interrupt request? We can use NVIC set priority, which basically sets the priority number 7. You can set the interrupt number 7 to a priority level 6. I'm going to show you how is this optimized, or how is this implemented. Let's open the SAM E54 file. This is the interrupt table for the SAM E54 board of microchip. So as you can see, these are, for example, these are the external interrupts. So these are the IRQ number. This number is what I'm going to use if I want to put the priority. So if I want to put the priority, for example, if I want the priority of the watchdog timer number 10 to be level 6, I would put here a 10. So this is the number that is the handle, or is the interrupt number that is used to give priorities, set priority, clear priority, etc. Right now we've known that there are something called priorities, and there are something called interrupts with higher and lower priority. So the code can be interrupted and can be continued execution. So what happens if you want to ensure that the code is executed atomically? Essentially, what happens if we want this piece of code to be executed with no interruptions? Basically, we enable and disable global interrupts. So in Zerynth ecosystem or in Zerynth Studio, you can use something like VOS syslock, which locks the system. And then when you finish this piece of code that needs to be executed, you need to unlock the system. And that's it. So between these VOS syslock and VOS sysunlock, you can execute this code with no interruptions, or with no interrupts, essentially. ARM provides some certain functionalities for the vendors of the microcontrollers. These are called synthesis functions. Something like NVIC enable, NVIC disable. These are all related to interrupt and interrupt priorities. So we're not going too deep into them, just giving a hint that these are all there to set the priority, to clear the priority, etc. So let's have a look at the a piece of code of an interrupt service routine, and how it is made, and how does the microcontroller, or how does the operating system know that the ISR has finished and it should go back to the code. So let's have a look at HPL USART HPL circum C. In HPL circum C, as you can see here, this is, I'm going to show you something. This is the serial handler for the UART of the Atmel SAM E54. So if we search for init, we're going to find that there is SPI init, SPI init. Okay, circum init. UseArt init, that's what I'm searching for. Okay, so in UseArt async init, which is the initialization of the UseArt referral, I'm basically disabling the interrupts, clear pending the interrupt, and then enabling the interrupt. These are the functions that I've just pointed out in the last slide. Essentially, I'm enabling the interrupts. So what happens when the interrupt is triggered? It will go to circum2 handler, which is this circum2 handler, exactly, circum2 handler, circum2 dev, circum2 handler. Okay, it will go to circum2 handler. So this is what is going to be executed. This is the interrupt service routine. So we are using a function called vos enter ISR, and a vos syslock, and then our routine, and then unlock, as we've discussed before, and then exit. So just to show you an example of the internal structure of these functions, let's have a look at vos exit ISR. What does vos exit ISR do? So what vos exit ISR is defined here, which is essentially port IR, which is essentially here. So this is for the ARM Cortex M0, this is for the ARM Cortex M4. Port IRQ epilogue, which is here, which is port yield from ISR. I'm just this tracing thing, I'm making it easier for you. Port and switching ISR, which is here, which is port yield, which will be executed here. So remember that we are talking about vos exit ISR. So if you trace the core stack of the vos exit ISR, you would land here essentially at port yield. So what does port yield do? It requests a context switch. So essentially, when I am writing vos exit ISR, I'm telling the operating system the interrupt service routine has finished execution. Start switching the context. That means look at the tasks that you have in the scheduler, start executing them based on what should be executed next on the priority, for example. So obviously this is a very complicated topic, so I'm not going to cover everything in it, but I've just given an example of vos exit ISR. So essentially vos exit ISR calls the scheduler in the operating system and tells it to start scheduling the tasks. I've finished the interrupt service routine, now let's continue with the other tasks. So for example, let's start the debugging time. So we've looked at the interrupts, we've introduced the interrupts, we've introduced the priorities of the interrupts, and then we looked at the vos exit ISR and what does it do. So let's have a look at a bug, and then let's debug this and look for the problem. During this debugging, we will find that there is some optimizations of the compiler. So essentially, whenever you're working with compilers and debuggers and linkers and that stuff, you have to know your tools. So I'm going to show you how we are debugging this piece of code. So this is the code. Let me connect the board and burn the code, and I'm going to show you the bug and how we could resolve this. Okay, so let's upload the code. Now it is erasing. Okay, so as we can see, when we load the new VM, the LED blinks and then stops blinking. So this is a interrupt example. So if we open, for example, Zerynth examples, if we open this, you and search for interrupts. So interrupts is here. So this is the example of interrupts. Basically, it attaches an interrupt on the button pin, which is the, in this example, it's button 0. So I am attaching an interrupt on this button. Whenever I press it, interrupt will be triggered. So is it triggered on the rising edge or the falling edge or both? This is defined here. So on pin fall, the interrupt will be triggered on the fall edge. On pin rise, it will be triggered on the rising edge. So when it goes from 0 to 1, this is the rising edge. When it goes from 1 to 0, this is the falling edge. So this is the example. Let's compile and uplink the code through Zerynth Studio. Okay, so let's open the serial console. So this is the serial console. Supposedly there is an interrupt attached on the button. So whenever the button is pressed, this function should be executed, which should print something and then blink the LED. But if we try it right now, nothing would happen. So the interrupts are not working. So, and this is the bug that we want to, essentially we want to look at, and what happens essentially. We want to look at this problem. So typically when we tend to face something like this, we will look at the head of the problem essentially, and then we're going to dig deep and then eliminate the options. So we are calling onPinRise, and what does onPinRise call? onPinRise essentially calls this function, which is onPinRise or full. So onPinRise or full eventually calls this, which is valPin attach interrupt. So essentially valPin attach interrupt attaches an interrupt on this pin, which is the first argument, to that function. So the first thing that comes to my mind when I'm debugging something like this is I should test valPin attach interrupt alone. I should put it aside and test it in a separate testing case. I've done that, and pin attach interrupt works fine. So this is not a problem. So what is the problem? Either the pin is not attached correctly, the mode, or the function, or something else. So let's have a look at the function that the interrupt is being attached to, which is val vm add irq slot isr. So this function, which is defined in here, essentially it looks, this function essentially what it does is that when the interrupt is triggered, it looks which interrupt is triggered and on which edge. So if the button 0 is triggered, that's okay. If this is the rising edge and I have configured the full edge, don't do anything. If this is the rising edge and I have configured the rising edge, then please execute the code. So the function, what it does is that it executes the specific code related to this specific interrupt. What is interesting is that it takes slot and direction. So it takes a slot, which is the number of the interrupt, and the direction which is either a 1 or 0. So we don't know what the source of the bug is. So we should look at how this function behaves on other boards, and then we're going to look at how does this function behave on our board, and then see what the difference is. So let's run the debugger and then see the behavior of the code. So this is the OpenOCD, which is the interface for the debugger, and this is the ARM GDB debugger. Let's connect target remote localhost. Okay, now we are connected to the board. So let's have a breakpoint at this function, which is vm add irq. Okay, so right now we have a breakpoint at this function. Let's press continue. So if we press this function, you would find that this function is called. So as I said, this function is called whenever an interrupt is triggered. And if we press continue, it would continue. But press again, the function will be called. As I said, press continue, you would find that the function typically is called twice, because this function should be called on the rising edge from the change of fall to rise and from the change of rise to fall. So this function should be called twice, essentially. If I press the button correctly, it should be called twice. So press continue and press the button. We're going to find that this is the first time that the function is called, and the second time the function is called. Do it again. First time function is called, second time function is called. What is interesting, you would see that every time the slot is number 15. So 15 is the interrupt slot for the button, which is correct. but the direction is 0. So this is wrong. This shouldn't be 0. This should be 0 and then 1, because as I said, interrupt is triggered from rising edge to falling edge, and then it is triggered again from falling edge to rising edge. So this should be 0 and this should be 1. This should be 0 and this should be 1. So right now there is something wrong with the direction. So let's have a look at the direction and see what's happening essentially. So the direction is an argument. So who calls this function? This function is being called here. This is the HAL layer of the Atmel software framework of microchip. So this function, this is exactly when I call the callback of this argument, I'm calling the function that we are referring to. So we are sending 15. I've hard coded it to be 15 for this example. So we are sending the slot, but we are sending the direction. So the direction should be either 1 or 0. Fair enough. But the direction is always 0. So there is something wrong happens here. So there is something wrong that happens essentially on the direction. So the direction is the output of GPIO get pin level. So we have gone from there is a error in the interrupts to there is an error in this line. So we have pinpointed the error exactly. So right now we know that there is an error in this line because direction is always 0 and it should be 0 and 1, 0 and 1. So why does this function return always 0 or always return 0? So the first thing that comes to my mind is to take this function and test it outside this code. When you do that, the function works with no problems. So there is a problem with using this function in this code. I'm going to show you the code and then we're going to see what the problem is. DIR, which is the direction, is an 8-bit character. So this is a variable that has a size of 8-bit, 1 byte. So supposedly I'm going to call this function, execute it, which gets the level of the pin, that is triggered, the button, and then the return function is the level of the pin, and then the return function should be sent back to the direction. So where is this function GPIO get pin level? This is in the HPL layer of the Atmel standard software framework. This is the implementation. So let's have a look at this function if it works correctly. So let's have a look at the compiler. So supposedly this function is being called whenever there is an interrupt because this function calls that function. So let's cut all of this call series and just go to this function directly. So let's go put a breakpoint on this function. Stop, put a breakpoint on this function and then press continue. So let's trigger an interrupt. Right now we have triggered an interrupt at GPIO get level because, as we have discussed, this is the function that is executed before the VM add IRQ slot. So as you can see, this function is executed. Let's press next, temp, let's press next, temp, and we are executing in here. But if I press another next, it will exit the function. This is very interesting because I'm not returning any value. So this function, which is the GPIO get pin level, essentially does not return a value. It is executed, but it doesn't return anything. So this is very strange. So why doesn't it return anything, although it is executed? On deeper look or a more concentrated look, this is an optimization from the compiler and the debugger. Because GPIO get pin level, if you look for the declaration of this function, you would find that this is a static inline, as we've discussed before, unsigned 32-bit. But we are using an 8-bit variable. So we are using essentially an 8-bit variable. So the question is, does it make a difference? So what we want to have is we want to have a 1 or a 0. So does it make a difference to have an 8-bit variable hold the value or hold the return value of a 32-bit value return function? Let's have a look at what the debugger tells us. Like, let's press continue and then trigger the interrupt again. So right now we are continuing the code. Let's trigger the interrupt and we are at the same function. Press next, press next. Let's print the value of TMP, and supposedly, so TMP is the return value because we are calculating TMP, which is the temporary variable, and then we are returning it. So in normal sense, this should be returned. But if I printed TMP, you would find that this is a very large number. If I print the hex of TMP, you would find that it is hex 83 and a bunch of zeros. So what happens here? What happens is that this is the return value of a 32-bit integer. But you're trying to put it on an 8-bit in an 8-bit placeholder, on an 8-bit character. So the microcontroller or the compiler basically look at this, and it looks at the first 4 bytes, and it says that the first 4 bytes are zeros, then the value should always be 0, and that's it. So essentially what the compiler has done is the compiler has optimized our code and ruined our code in the same way. So the compiler has optimized our code because this function returns a 32-bit value and you want to put it in an 8-bit variable. So what happens is that it looks at this variable in this line, it finds that the first 4 bytes are zeros, then the result is going to be always 0, and then it's not going to return anything. And this is an optimization thing. So essentially, the compiler said, I will execute the function because you told me to execute the function, but I will not return any value because it's always going to be 0. So what is the solution for this? The solution is to just return a 32-bit value. And that's it. So let's compile and uplink. These kind of errors are related to how the compiler is written and how is the compiler developed. So these kind of optimizations, although they might slip during development, but these are very important because they are trivial. Essentially, if I want to show someone what's happening, this function is a 32-bit and its value should be put in an 8-bit. But the compiler basically decided that it's not going to return anything. So it's going to execute the function, but it's not going to return a value. So let's compile the code and then uplink and then upload the code and then look at what happens if we put a 32-bit value instead of an 8-bit value. Okay, it takes a long time because we have configured the compiler with the with the compilation options of code size, essentially because it's, as I said, it's important. So the compilation time is not really the best. Okay, so let us stop the OpenOCD. Let us quit the debugger, uplink the code, erasing, programming. Okay, so let us upload the same example. And then open the serial terminal. Okay, now if we this is the same example and the same code. If we press the button, you would find on the serial terminal that it printed touched, which is the ISR, so it is triggered exactly or as it should, and the LED is blinking. So we fixed the bug essentially. And the best part is looking at the debugger after we fixed the bug. So let's open OpenOCD again, and let's look at the GDB debugger and look at what happened essentially. Localhost. Okay, so let's look at the function which is vmirq slot. As you can see, when we are when we had the bug, essentially every time, as I said, it's called 2 times every interrupt trigger, but it was called with a direction of 0 every time. So let's have a breakpoint on this function and then press continue. Let's trigger the interrupt. You would find that it is triggered on direction 0, which is okay. But if you press continue, you would find that it's triggered on direction 1, which is what we have set. So we have successfully fixed the bug essentially. So just to sum up, what was happening is that we were trying to cast a 32-bit variable or a 32-bit return value into an 8-bit. So the compiler basically optimized this into looking at the variable in the middle and then saying, okay, I'm going to execute the function, but I'm not going to return any value. So this was a very interesting bug. Let's have a look at another bug. Essentially, let me ask you a question. What is better, to use Boolean, like Boolean X, so it should hold 2 values, 0 or 1, true or false, and then execute a function and then cast this value to a Boolean, or X and then execute this function and then use the item this operator, which basically checks if it's a 1, then put a 1, if it is 0, put a 0. So what's the difference between these essentially? The question is, what's the difference between using bool and using this operator? The difference is that in the compilation time, the difference Boolean is developed somewhere and is written somewhere in the compiler according to the documentation of the compiler. So Boolean, in many compilers, Boolean are declared as any value other than 0 is a 1. It doesn't have to be 1. And that's the problem with Boolean, because Boolean doesn't have to be 1. So if the value of Boolean is 10, then it's for Boolean it works with no errors. But for your function, you might be expecting a 1 from it. So the second implementation, which basically checks if it is anything, so put a 1 instead of it, is better, because you're not relying on the Boolean implementation. You are 100% sure that the result of this optimization is a 1 instead of a 0. Okay, so we have a question on the chat. If you have questions, feel free to add them on the chat. Would it be possible to be notified of this problem during compilation time? It will be possible if the interrupt driver is written in a way to assert, basically to check if, like as we've seen in the GDB debugger, basically this function gets called with the rising edge and with the falling edge. So if the driver is designed in a way to assert, to check for these values, it should be notified during compilation time essentially. And Giacomo says that I don't like Boolean. Yeah, Boolean is not really the best implementation to use. Okay, so the last thing in our presentation is some interesting C code snippets. So we're going to see some C snippets, and then we're going to look at what's wrong with each of them and how we could fix them. So I'm going to give you a minute to look at these C functions or C codes, and then we're going to go over them, see what's wrong with them, and then fix them. And feel free to, in the comments, to leave your questions or answers. Okay, so the first is a function like macro. So macros in general are text replacements essentially. So this function, if it is thrown into a C source file, it will compile with no errors, and it will work with no errors, given that you give it numbers only. But if you give it expressions such as if A equals to a mathematical expression, this could lead to some problems, because the main difference between functions like macros, which is the minimum here, and functions is that the functions check for the input argument. So the functions check whether the argument is integer. Have you actually supplied an integer to this argument or not, or have you supplied something else? Whether the functions like macros do not check for any input. It basically replaces what's happening. So since we are using this operator, which is less than, this operator has an order of operations. So in C, there are the order of operations that basically is the square brackets and the parentheses, and then the square brackets. And there is a list of operations that should be executed before each other. The power, or the brackets before the power, and the power before the multiplication, and all of that stuff. So the problem with functions like macros is that it's text replacements. So if we put functions, or we put mathematical expressions here, this might break the code essentially, and there's no way to know that for sure, because unlike functions, they don't check for the input arguments. Okay, and for the second function, essentially volatile means that this is something that the microcontroller has to fetch regularly. So what does volatile keyword means? Volatile means that this value could be optimized somewhere else, could be optimized, for example, by an interrupt service routine. So what are the typical volatile values? For example, the register locations. So in this microcontroller, there are peripherals such as the timers, such as the GPIO. The peripheral location, the memory address of this peripheral, is always a volatile, because the value of the register can change by any other piece of code. So it's always defined as volatile. The third example is the align to bits. So by a careful look, you would find that it basically takes an address, casts it, and then makes a bitwise AND with the bits shifted, with one shifted the number of bits. So let's make an example. I have an address of 10,000 hex, 10,000 hex, and I have a bits of 5. So there is a 1 shifted 5 locations, and then I'm subtracting 1. By subtracting 1, I'm actually doing a 0 and then 1 1 1 1 1 1, and then I'm doing a bitwise ending. So I'm taking these bit locations, which are with the ones essentially, and I'm leaving the rest. I'm not concerned with them. The problem with this function is that it doesn't have a limit on the number of bits. So for example, the address might be 10 bits, but you are shifting a 15-bit, or you are shifting a 20-bit. And this problem is actually taken from an SDK of a major company. So these kind of problems slip into when you're developing when you least expect it, because there is no kind of error. There's no way to know for sure what's happening unless you debug your way through it. So the problem with this function is that essentially there's no limit on the bits, and because bits are shifted to the right, so you can have an address of 12 bits or 18 or 32 bit, and you can shift it to a 33 bit, and then everything will be messed up essentially. Okay, there's a question: how do we fix the hash define and number 1? So how do we fix the hash define minimum of A and B? We fix it by putting a parenthesis around A and B. Why? Because the parenthesis has a higher order of operation, so it will be executed first. That way the expression will be executed first. That way it wouldn't mess with the other operators, which are the less than operator. Now the fourth example, which is the always return 0. So this function has a name of always return 0. and it takes 2 pointers, integer pointers, A and B, dereference B and put a value of 0 in it, and then dereference A and put a value of 42 in it, and then return the value of B. So there are 2 problems with this example. The first problem is that this is not a this is not executed atomically. So essentially, you can, for example, put a 0 in B, and then an ISR changes something or changes the value of B, and then you return B, which is something else. So how do we solve that? We put this in an enter critical section and leave critical section, or VOS syslock on VOS syslunlock. Essentially, we need to make sure that no interrupts and nothing else could change the value of B. So this is the first problem. The second problem is that this function is called always return 0. But does it always return 0? That's the question. No, it doesn't, because I might supply B, like I might supply the same variable in A and B. I might send this function the same variable as argument in A and B. What it does is that it would make the first argument 42 and return the first argument, essentially, because I've just added it to 42. So what I want to say by this example is that the function has 2 arguments, but that doesn't mean that they're always going to be a different argument. They might be the same variable. There's no problem with that. And this is another runtime error which you might not notice during the compilation, but during runtime, you're going to have to debug your way through it, essentially. So this is a summary of what I've said. Non-atomic operations, critical section, leave critical section. So in this presentation, we have talked about certain concepts such as real-time operating systems, such as firmware code size optimization. And then we needed to debug a problem with the interrupts on the Atmel SAM E54. So we introduced interrupts. We looked at how are interrupts implemented on the Cortex M4 microcontrollers and the Cortex M4 based microcontrollers. And then we looked at some interesting C code snippets, some interesting tricks in C, essentially. So feel free to leave your questions and feel free to leave your comments on the chat, on the video, and thank you.